All right. So the next two things that we have to look at is we have to look at how waves behave. The last two phenomena is diffraction and interference, right? We looked at reflection already and we looked at refraction, right? We want to finish up the wave phenomena today, right? Waves undergo something called diffraction and they also undergo something called interference, right? So if you look here, you have a little definition and two examples, right? This is in the handout I would have sent earlier. Hold on, I'm going to send it back. Yes. All right, good. Everybody have it, right? So diffraction occurs when you have waves, right? So imagine you have a wave there and the wave is trying to fit through that little space. Hold on. Right, so you have this little gap here and you have a wave and the wave is trying to fit through that space. What will happen is as the wave passes through there, it will kind of spread out. And that spreading out is called diffraction. Okay. So diffraction occurs when a wave passes through a normal aperture or opening and thus spread out over a large area as it continues to progress. All waves undergo diffraction, right? But what you will learn about diffraction is that the smaller the opening, look at here, the smaller the opening when compared to the wavelength, the greater is the diffraction, right? So it is difficult to observe diffraction of light because of its small wavelength, right? So special equipment has to be used. And if you look here, if you look at these waves, right? The waves that went through the larger opening, right, didn't undergo as much diffraction. But the waves that went through the smaller opening underwent a greater amount of diffraction, right? So diffraction is also dependent on the opening, the size of the opening, right? When compared to the wavelength. Okay, so that's the main thing that we have to learn about diffraction. As I said, the diffraction is very difficult to observe, but if you all go into Cape Physics, there's something called a diffraction grating, right? Is one of the instances where you would observe it. So it's like these pieces of glass with real small openings. And when light passes through, the light will split up into all its colors, right? Anybody remember all the colors white light is made up of? Anybody remember the acronym? Right, Roy G. Biv. Right, Roy G. with white light is made up of red, orange, yellow, green, blue, indigo, violet, right? And all these colors when combined give you white light, right? And of course, they all have different wavelengths, right? I'm not sure if I told you this during refraction, but they all have different wavelengths. So when they undergo refraction, like when you try to pass white light through a raindrop, for example, it undergoes refraction. And because of the different wavelengths, they all travel at different speeds. So what will happen is that the white light forms a rainbow, right? Which is as a result of refraction, right? I'm not sure if I mentioned that during refraction, but white light is split up into all those colors there. Anyway, if you stay here, let us make a note right now, please. Roy G. Biv. That's the acronym, right? Okay, nice. Just a little theory that we need to know, right? We need to know about scientists and how they view light. You see how we view light as waves? Well, light is not truly waves alone. Light is also made up of particles. So when you view light as a wave, right? The correct way to view it is that yeah, it is waves, but it's also particles. So if you view light, you can view it like a wave made up of all these particles. But in light, we kind of see the wave part with the wave properties more. In a tennis ball, for example, we see the particle properties, but a tennis ball also has wave properties as well, right? As you go deeper into physics, you will learn all those theories, right? Right, but we need to know about these four scientists and what were their views on light. So Sir Isaac Newton, right? He said that light is a stream of particles called corpuscles. Huygens, he said light is a transverse wave, not particles. Thomas Young, right? Light is a wave that can undergo interference. And Einstein, light behaves as both a wave and a particle, right? So this is the theory that we kind of stick with now. Light has both wave and particle properties. Everything around it has both light and wave particle properties. It's just some of them we could see the particle properties. Some we view them as waves alone. But they all have properties, just one more dominant than the other. Okay, so if you see something called the wave particle duality, right? It simply means of light. It simply means that light has two sets of properties, right? Right? Light has two sets of properties, wave properties and particle properties, right? There's an experiment called, oh, look at it, right? I was looking for this. There's an experiment called the photoelectric effect that was used to highlight this, right? So Einstein also came up with the photoelectric effect, for which he won a Nobel Prize. And this photoelectric effect was the phenomena that produced, was the phenomenon that he was able to show that light has both properties, right? In the photoelectric effect is a phenomenon that produces electrons when light is shone on a metal surface. So he had a metal surface and he shined light on it. And when the light hit the metal surface, electrons left and the electrons move away, right? Ideal examples of these are digital cameras and solar panels, right? This one experiment was the experiment that converted classical physics into what you study now called modern physics. So this one experiment changed the entire course of physics from classical to modern. And to summarize, classical physics is where people had thought light had wave properties alone, and modern physics is where light had both wave and particle. Right, this is plenty theory, so I hope you all don't find it too boring. But it's just some theory giving us some background where and how physics changed, right? But they're still hidden, Faith.
Yes, sir.
All right, nice. Let's see what Christian said. Say if electrons leave when light hit metal surface, would that object be? Well, technically, yes. Right? It'll be heated as well. Is a process where a lot of heat is absorbed by the material. Right? But the electrons gain most of the energy, and the electrons is that energy is what the electron used to break the bonds. So technically, yes. If you look at something called a photoelectric cell, you will see it happening. You can always Google it when you have time. A photoelectric cell, it shows you how this photoelectric effect happens. Right? This entire topic you'll do in Unit 2, physics. All right, where was I? In digital cameras, the photons are of different strengths, which produces variations of brightness and color to translate in a photographic image. All right. The next phenomena, no calculations for this phenomena. For diffraction, all you need to know about diffraction is definition and how the size of the aperture affects the spreading of the waves, right? If we look again here, smaller it is, the greater the spreading. The next one that we have to do is called interference, right? Normally, if you were in class, I would have made you all I would have made you all draw over this diagram, right? I'll tell you what to do, so you'll have an idea of what to expect, right? But I'll use this one in class today. All right. So what is interference, right? I'm not sure if you'll ever observe it. Maybe if you look in your room now, there might be points where you have two lights intersecting. So you have light from two bulbs or light from your window and a light from a bulb intersecting. Where they intersect, you might see points where the light is brighter, and you might see points where it's dark. The points where it's brighter is called constructive interference. The points where it's darker is called destructive interference. Constructive interference produces larger waves. Destructive interference produces cancellation of waves. All right? And it's basically a match thing, right? So watch this here. Interference occurs when two waves superimpose with each other to form a resultant wave that might either raise or lower the amplitude. There are two types of interference. Well, there are more than two types, but for now, there are two types of interference, constructive and destructive. Constructive, you have two small waves. Let's pretend the amplitude here is A. When you have two waves of amplitude A meeting, they produce a larger wave of amplitude 2A. Anybody remember what is called two waves? those two waves are said to be what? In phase. Very good. Very good. In phase. So whenever you have two waves of equal amplitude at in phase, you end up with constructive interference. Whenever you have two waves that are out of phase, whenever you have two waves out of phase, right, you end up with destructive interference, which is like canceling out. So if you look here, you'd recognize a crest meeting a crest and a trough meeting a trough, right? When a crest meets a crest, you have a larger crest. When a trough meets a trough, you have a larger trough, right? Here now, a crest meeting a trough. When a crest meets a trough, you end up with 0, right? Think of the maths behind it, right? If this value is A, this value down here will be minus A. So when A overlap with minus A, you'll get 0. Right? When A overlap with A, you'll end up with 2A. Right? That's the concept of constructive and destructive interference. And there was a guy who did an experiment called Thomas Young. He did the double slit experiment that illustrates constructive and destructive interference, right? Right, there was something yes, I gave you all this small little thing when I was explaining phase difference. Right, destructive interference has the waves being out of phase by exactly lambda and 2. But remember that? They differ by a half a wavelength. So this wave, and this wave, they differ by half a wavelength. Remember? So like half a wavelength after, this now happens. So they're said to be out of phase by half a wavelength. All right, nice. Let's take a look at Young's double slit. Then I will show you this simulation, right? Right, so watch it here. Hold on. Right, so you have light, and you have light going through a single slit. The purpose of the single slit is the light sometimes doesn't produce light or waves of one wavelength alone. So when you put the single slit in front, it's a kind of filter. So it kind of filters and give you light going into the double slit of the same wavelength. Double slit simply means, I don't know if you all seen it here, but they have two openings, right? And when the waves go through there, if you're not seeing it, tell me, right? But when the wave goes through the first opening, it will undergo diffraction here. Next one will undergo diffraction here. And by coming through here and here, right? Right, the next wave through here will be here. All right, hold on. I'm gonna just show it here first. And then I will draw over those in red and blue. Right? Normally that's what I'll make you do, right? So you have a wave here and you have a wave here. Right? Then you have a next wave coming through there, and you have a next wave coming through there. Right? Then you have a next wave coming through there, and a next wave coming through there. Oh, sorry, that one was bad. Next wave here. Always make sure they have the same distance between them, right? Right. What I will normally make you do, right, is every other wave. I'm gonna show you what I mean by every other wave. Every other wave, I'll let you draw it in blue. Oh no, what's that? Right? So one will be a crest, one will be a trough. Crest, trough, Press that next trough here. Hey, not looking too good, eh? Actually, not looking real bad. Give me 1 second there, earlier. Let's draw it back properly. Right, the purpose of highlighting it like that is that you would see crest and trough meeting, right? And then you'll be able to identify destructive interference, right? So I am going to do it here. Bam, bam, bam. Right, this is something nice how to do with a protractor. Nice and neat. Pew, pew, pew. Pew, 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 pew. Okay, so try to give you one set there, right? But let's change back the color. Right. So if you look there, you have a set of waves, right? Right. The black waves are crests, and let's say the blue waves are troughs. Okay. So look at when. Right. It's not too perfect, but look at this here. Look at this point here, where the crest and crest meet. There's a trough and trough, crest and crest, trough, crest and crest again, right? Along that line, watch it closely. That line where all of those meet, crest and crest, trough and trough, crest and crest, producing a white band. So you are going to observe a white band and a dark band. The white band is as a result of constructive interference. So along that line, everything you observe is constructive interference. But watch this here. Where to start? Right, look. I didn't get too much, right? But if you look here, crest and trough, crest and trough, crest and trough, crest and trough. Along that line is destructive interference. Okay, you're seeing that? You'll see now there? So the points where the black and the blue meet, that's destructive interference. Okay?
Yes, sir.
You'll see. Right. So what I want you to do, it will take a little while. I want you all to do this for homework from, all right? Do the double slit. It must be with a what's called it, boy? It's a compass, right? With a compass, I would like you to measure it out properly. So like you first thing, take a ruler and measure, I think you measure 5 millimeters, right? 5 millimeters apart. And I want you to you could use a solid line and dotted line. Do a crest, trough, crest, trough, right? And do the same thing on the next side. Right? Crest, trough, crest, trough. And I want you to go, actually try this now for Molly, because I know some Molly mightn't even touch his book again till next week. Right? Get a compass quick and do that for me. Don't go too far. Do about 1, 2, about 1, 2, 3, 4, 5. About 5 pairs of crests and 5 pairs of troughs. And where the crest and crest meet, kind of line it up. Same way I showed you all here. Crest and crest, trough and trough, crest and crest, trough and trough, crest and crest, crest and crest. And connect them with a line. And where all meet and you draw the line out, that'll be a right spot and a constructive interference, right? I give you now 10 minutes. Do that for me, please. Right? When you finish, you take a little pick and send them on WhatsApp. Right, Shannon? Right, so remember to separate it by crest, and you could use a dotted line for the trough. Right? If you want to change color, you could do one red and one blue. Okay? And any key you want. Can Shannon, you're lying. Your phone camera working good. Do the thing for me, please. Right, just do that fast and all, because if I give you homework, you won't do it. That wouldn't take you long. Right, it's just to highlight interference and all the constructive interference point and destructive. Try to make sure the spaces between them equal as well. Okay, 10 minutes. Try that fast. Anybody get you with the diagram?
Yes, sir.
All again, sure. All right, nice. Right, so it's important that you could put that together, right? You all got it, right? And once you do it properly, with the right spacing between the waves, you'll be able to it'll line up perfectly. Right? Might be a little off because yeah. Right, it might be a little off if that's not working out. Okay, nice. Let us continue. Shannon, if finish. Basically, all right, let me just message. You're not joking. I got a message in mother and she just check that for me. So she reach you. Aha, Sebastian sent something from her there. Sebastian, what kind of crazy looking thing is that? I tell you to use a compass, Sebastian. If you do use a compass, it wouldn't line up properly. Anybody will send a picture of this? That wasn't done freehand? Oh, Karina, no see anything, right? I'll read it for you, that's not right. Okay. So when waves are in phase, constructive interferences happen, crests and troughs are aligned, and they result in bright fringes called maximals. When the waves are out of phase, destructive interference occurred, and they result in dark fringes called minimals. Troughs of one state cancel out crests of the other. Okay. Shadows are considered proof that light travels in straight lines. That's one of the things that they ask you to prove sometimes, that light travels in straight lines, right? And if you observe that once you have an object in front of light, the light can't really go around it, right? So only the light that travels in straight lines and doesn't hit the object is what we'll see, right? So light travels in straight lines. Anybody remembers, and I remember this when I used to teach Form 1 integrated science. Anybody remember the experiment that we would have used to show that light travels in straight lines? We had cardboard. Pinhole camera was an example, yeah. But there was an experiment that we had used to show that light travels in straight lines. We had 3 pieces of cardboard and we had the holes aligned at the same point. Right? So when the light travels through the holes, right, provided they're aligned, they will be able to view the light on the opposite side. But if you were to adjust any one of them, right, you wouldn't be able to see the light. And the conclusion was light travels in straight lines. All right, so that's a quick thing there to look at. Okay, so those are the wave phenomena. Just one more thing I want to talk to you about before we move away from here is if you look here, right? The pattern, this pattern here is affected by, nice, Sebastian. Oh, okay, piano. Right. If you look here, there is you see this pattern here is affected by by three quantities, right? The distance between the screen and the slips, the spacing between the slips, and the wavelength coming in. Those three things affect the pattern here, right? Hold on, I'm gonna see if I get the simulation to work. I just wanted to show you all that. If you're not seeing or hearing, you'll let me know. This one is be a little harder to see it. Hold on. All right, watch this one here. Let's see if we can see it. Okay, I can't control that. Not too hard for me to control. Right, how do I put the double slit again? This is not the one with the image. Hold on now, yeah. So what you're observing there is diffraction, right? Look how the wave bend in there. Right? What you're observing is diffraction. Okay. I'm going to put the two slits now, but I want them closer together. 1 second, Taylor. All right. I guess that's the best we could do it, right? And I want to just decrease. Why is this wave so big? Right? So what I'm trying to do here is along this region, see if we could find constructive and destructive. All right. Forget the simulation, right? Look at here. That's not it. Look like I can forget too. Let's see. All right, this is the one with the double set. Not to write these things down. So this is the one that this is the one that I made you draw just now, right? So if you look, it have points of constructive and destructive. If I were to bring the if I were to bring these double slits closer to the screen, look at what happening. It making the light and dark closer together. Focus on the fringes, right? Focus on the last screen, right? So if I bring the slits closer to the screen, you'll recognize that the slits coming closer together. If I were to bring, hold on. If I bring the slits closer together, look at what happening there. The light and dark fringes, they're getting larger. If I were to bring them further apart, you'll recognize that the light and dark fringes, they're getting smaller. Okay? And if I were to change the wavelength, hold on. So I'm gonna change the wavelength to about 480, 500, you'll recognize. As I decrease the wavelength, the slits coming closer together. As I increase the wavelength, the slits, you'll see that, the slits getting spaced out some more. Remember, all we're focusing on is this, right? Just focus on that. And I want you to focus on if this space getting larger or smaller. Okay, so watch it again. I'm making the wavelength bigger. Notice the space getting bigger, right? I'm gonna make the wavelength smaller. Look how much smaller the space getting. Right, so wavelength affecting it. The space between the slits affecting it. And how close the double slit is to the screen. You see, all those things affecting it. Y'all okay with that? Darian?
Yes, sir.
Right. All right, so those are the three things that affect the fringe pattern. Okay? All right, so nice. We observed the diffraction and interference there. All right, a nice job you done. Right? If it just do a few more you done, you would see a lot more constructive and destructive, right? Your diagram look nice and neat. Right? So that is your interference, that is your diffraction and your interference. All right. Oh, I now understand, Sebastian. I now understand. I wanted to pay attention to draw a diagram like that. Good. That's a good excuse. Better than Shannon excuse. All right. So that is all the things that we have to look at with waves, right? All these little things here, things that waves undergo. I want you all to read it over. Make sure you have a little idea. Not a little idea. Make sure you know everything. All right. Before we move on to lenses, actually lenses is what we're going to focus on next week, right? We're going to focus on lenses. That is here, right? I want you all to read up on concave and convex lenses, and you will need graph paper because we're going to draw over all these diagrams. Okay? We're going to draw over all those diagrams. So you'll need graph paper to draw that, probably like 3 graph pages. All right, before we move on, we have been focusing all our attention on light. We need to also know about sound waves for CSEC as well, right? So sound waves is an example of a longitudinal wave, right? We have been focusing on transverse waves. The good thing about sound waves is that they undergo the same thing. They undergo reflection, they undergo refraction, they undergo diffraction, and they undergo interference, right? When you all finish this class, just to make sure you have an idea of the 4 phenomena, you should close your book and try to write down the 4 phenomena in your own words. What is reflection? Draw a diagram if you could. Refraction, diffraction, and interference. Right? Make sure you understand the different phenomena. Right? Sound waves. So I'm just going through this here. Sound is transferred by longitudinal waves that are mechanical in nature, meaning that they require molecules or a medium for their transfer. They are unable to travel through a vacuum such as space. So for example, if something happens in space, we can't hear it. We're able to see it because light can travel through a vacuum, but we can't hear it because sound needs a medium in which to travel. Okay? The presence of more molecules and enables sound to travel for faster, right? Enables sound to increase its speed. This means that sound will travel faster in denser medium. So if you look here, right? Right, bye. Sorry, so air, look at the speed of air, look at the speed in water, and look at the speed of sound and steel. So sound travels much faster in steel than water and air. Okay, there's some approximate speed, right? There's a little experiment to show that light needs sound needs a medium to travel. There is the Bell experiment. So if you put a bell in here and the bell goes off, you'll be able to hear it, right? But if you pump all the air out, right, and the bell goes off, you wouldn't be able to hear the bell. You'll be able to see the bell going off, but you can't hear it, right? That's a simple experiment to show that air needs a medium in which to travel. Okay. Wait, now I didn't all the talking today. I'm gonna start to ask all some questions. Right? So sounds have different pitches or volumes, right? And the pitch of a sound is dependent on the frequency of the sound, and the loudness is the amplitude. So the larger the amplitude of the sound, the louder it is. Sorry, the greater the amplitude of the sound, the louder it is. The higher the frequency, the greater the pitch. Okay? So a mouse's squeak has a high frequency, low amplitude. So a loudspeaker bass has a low frequency, high amplitude. Okay? So we need to know those properties about sound waves. And when you hear the term quality is a mixture of that, right? Is a mixture of the right frequency and the right loudness and the right amplitude, right? So some people you'll recognize have different qualities. Like some people might like sounds with real plenty bass, with plenty loudness. Some people like it with a high pitch. So people qualities might be a little bit different, right? We need to also know the range of audible frequencies, right? This is the range of audible frequencies. So the lowest frequency we could hear is 20 hertz, largest 20,000. Any wave with a frequency higher than that is called an ultrasound, right? Ultrasound waves, you all may have experienced it already, right? Actually, I experienced it today. Ultrasound waves have numerous practical applications, including the observation of fetuses in their prenatal stages, ultrasound cleaning, and probing materials for internal flaws. Also, ultrasounds are used to help repair muscles, right? So there are plenty of uses for these ultrasounds. Sonar, here's an example of sonar, right? Sonar, as you can see here, is that we could use sound waves, right? We could use sound waves to determine the depth of the ocean bed, right? Of course, your transmitter wave, the wave is reflected, and we measure the time taken for the wave to go up and down. And then we could use the formula speed as distance and time and work out the time. Sorry, work out the distance, which is speed by time, right? Of course, we will know the speed of the waves being emitted. Okay, and that way we could get the distance. Of course, you gotta be careful in the calculation with time on it, which I'll show you in an example. Right? Sonar, which is sound navigation and ranging, is a technology that uses ultrasound pulses to determine distances. It does this by measuring the time it takes for a fired sound pulse of a known speed to be emitted from a transducer, echo from a surface, and be received by the detector. The formula is given by 2D and T. Anybody could tell me why they put 2D on T? Why they put speed as twice the distance divided by time? Anybody has an idea why?
Because they're going back and forth.
It's the same example we're talking about here, right? Why is the formula 2D on time? Go ahead. Somebody was saying something. Right. Darian said because the echo is going back and forth. So the echo, remember we here in the echo, we measure in the time for the echo to come, right? And that echo would have traveled down, which is D, and back up, which is also D. So that echo would have traveled 2D. And the time that we have is T. So speed is 2D and T. All right. And of course, you rearrange your formula and you find for a distance. All right. So here you have an example. If the speed of sound in water is 1600 meters per second, and the time taken for the sound pulse to hit the seabed and return is 400 milliseconds. Remember, ms is milli, right? Determine the depth. So you will notice I use this formula here. Well, not me, the person uses this formula here. All right, work it out, divide by 2, and they get a distance in kilometers. Okay, and that's simply how sonar works. All okay there? Yeah, Adele, are you okay there? Kareem?
Yes, sir.
All right, so that's the concept there of waves, light waves, and so on. That's song waves, I mean, that's everything you need to know about song waves. The next type of waves I need to know about is electromagnetic waves, right? This is a type of transverse wave again. The bad thing is you have to learn all of this, right? You have to know the frequency that they all operate at. So electromagnetic waves are waves that have both electrical and magnetic properties, right? You have to know all of them, their names, and you just have to know the frequencies as well, right? But if you look here, it shows you how they change via wavelengths. Oh no, what has happened there? I lost the page. Right? I just lost the page, right? So I want you to spend some time and learn this, right? The electromagnetic spectrum, the largest is radio, smallest is gamma. So it goes from radio to micro to infra to visible to ultraviolet to X-rays and gamma. Right? The way I kind of remember it is I would always remember radio is the biggest, gamma is the smallest. and visible light in the middle. Around visible light, I'll always remember Roy G. Biv. So I'll always remember that infrared to the left of visible, and will of course violet to the right. And then I have two more to remember, microwave and X-rays, and easy, right? Because X-rays, small, so X-rays go in here, and microwave is here. Right, so that's one way to remember it. Radio is the biggest, gamma is the smallest, visible light in the middle. Remember, visible light is made up of infrared and ultraviolet. Roy G. Biv. So red is bigger than violet in terms of wavelengths. And then the remaining, microwave is bigger than X-rays. Right? That's the best way to remember it and put them together. Right? Sometimes they ask you to, I remember one year they asked you to complete this whole thing. To write down I don't think it was wavelengths they wanted frequencies. Right? From the smallest to the largest frequency. But just learn one of them. Right? Because they all travel at the same speed of light. So once you know speed, right, all you have to do is learn the frequency or wavelength, and you can figure out the next one. Right, so those are the things that you need to learn, and then we'll have a little table there showing you the application of each one of them, right? Okay, so for the waves part of it, that's it. Those are all things that we need to know about waves. All the wave phenomena, right? We need to know about all the wave phenomena, all the characteristics of waves, right? Oh, this table I'd given it before, right? So you need to know the difference between all of them, right? You need to know all your wave phenomena, sound waves, electromagnetic waves, and everything about light waves, right? All the theory, everything about light waves. And then once you do that, then we could jump into lenses, right? Did I talk about this? When you plot sin I versus sin R, the gradient is the refractive index. I think I don't want to make sure I didn't leave this out. When I was talking about the glass block experiment, and you read off all your I values and your R values. I remember that? That would have been 3 weeks ago. Anybody remember that? Okay. Faith remember, so good. We have some hope there. We have some faith that you all remember. Right, so good. So that is your lenses, your waves, right? Next day, we're going to spend some time on lenses, right? Because I do plenty talking today, right? So I wouldn't bore you anymore, but I want to give all you a little test. I'll give all you a little multiple choice Kahoot next on all these things, right? But next day, we're going to focus on convex lenses and how to determine the image produced by convex lenses. So if you look here, you have an object going in a convex lens, producing an image. We're going to learn about all these things with respect to our image. And then that's it. That will take us to the end of lenses. The end of lenses and the end of waves, right? And then that'll be the end of unit, or the end of CSEC physics for those who were with me for the past 2 years. Then we're going to start over. Right, in starting over though, what I will do is I will start a poll, and we will take a look at the topics that you all found were difficult. Right, I'll start with that to revise that and then start to go over everything. Okay, so I want you to spend some time. Yeah, lenses is next week. I want you to spend some time and go over, start revising. Start creating your own little summary sheet. You could use this person notes. I would have given you notes for other things, but you could use this person notes and you can start going over everything in here, right? Start going over all these little things. And then we will take a look at the hard topics and do a lot more past papers. right? I feel like I didn't do plenty past papers in waves. So I want to go back through all those years and make sure we cover a lot more past papers. Okay. By chance, anybody have a sub copy of a topic by topic past papers in physics? Like I would have done for AdMaths and well, that we have for AdMaths and maps.